So in this video, we are going to talk about the importance of water quality in water management and the various parameters that characterize water quality and some issues that affect the water quality. Water quality is critical in water management as it affects the way we use water and also it influences the overall condition of our hydrological system. So what is water quality? So water quality is best described as a measure of the condition of water. Or more specifically, we refer to the condition of water in terms of physical, chemical, and biological characteristics. And this determines the fitness of this water to a variety of applications or uses. So let's take, for example, our water cycle here or hydrological cycle. So basically, naturally, we have a water cycle that goes with the process of evaporation coming from the reservoir, from sea, for example, from dams, and then due to the process of evaporation, it goes towards the atmosphere, and then it's stored there in the form of clouds, for example, and then later on, the clouds will precipitate into the form of rain and snow. So this rain and snow goes back to the ground, and then the liquid there penetrates the groundwater, our ground, and then goes to our groundwater. And then again, some go back to our reservoir, and then the process repeats again. So that's the natural water cycle that we have. But in many years now, because of the human activities, due to the improvement in technologies, due to the advances in many processes, you can see that there are a lot of human activities now. And this human impact, the anthropogenic impact, has resulted to the varying or the changing of water quality. So for example, in this case, we have a wastewater treatment plant here, we have a drinking water treatment plant here, and we're also coming from the houses. There are discharges here. This one is discharged to the river, for example, coming from a wastewater treatment plant. So the quality of this water that is discharged here affects the receiving water. On the other hand, there's also a stormwater discharge over here. And you can see other discharges as well coming from the agriculture as a runoff. So when you say agriculture, it contains some fertilizers, some nutrients that go to the receiving water. And even some waste coming from animals also go to the receiving water. So what happens now? So the quality of the receiving water will definitely change because of the influx of some masses, some new addition of different contaminants. So in this case, we can describe these different sources of pollution as a point source. A point source is something that is easy to identify because it is coming from a single source or something that is fixed. For example, in this case, it is coming from a discharge from wastewater. So it's a point source. So we'll be able to identify the quality of this source. However, the other one is a non-point source. So in this case, an example of that is this agricultural runoff. So it is coming from different places. So it's not only a single source. The waste from the animals also is contributing to that. So this is harder to identify in terms of its quality because it's coming from different sources. So from this from even though we have all this human activity, in natural case, the quality of water, there is no such thing as pure water. So let's say in a natural cycle, we don't see or we don't say that there is a pure water that naturally exists unless you are working in a laboratory. So pure water is the pure water is something that has nothing inside the water, like there's no minerals there, there are no other constituents in the water. So in natural environment, especially for example when you have rain, so rain could be possibly as pure as possible, but what we can see from here is that during the precipitation, there are some gases or some other things, contaminants from the atmosphere that is absorbed or that is dissolved into the rain. So the rainwater quality has some impurities already, some impurities on the water itself. But it doesn't mean that impurities, natural impurities, will inhibit people to use that water. In fact, they are okay to be used. The as long as they meet the standards of the specific uses. The main problem is the one that is coming, the discharges that are coming from human activities. This is the main problem. These are the wastewater coming from human activities. Wastewater in the form of the sewage here has many impurities that are added. This is in more added value. So it means the water quality in wastewater is much different from the natural impurities that is involved in the mixture of natural waters. So the wastewater is basically divided into two kinds. We have the domestic wastewater. Basically, domestic wastewater is coming from mainly from the domestic use. So this is coming from the houses and some commercial buildings as well. And the other one is the industrial wastewater, which from the name itself is coming from industries or manufacturing industries. So between the domestic and industrial wastewater, domestic wastewater is more predictable in quantity and quality. So it is easier to address this quality and quantity. When compared to industrial wastewater, industrial wastewater are more variable in its quality and quantity because of the differences in industries. So those two wastewater are our main concern, especially that they're coming from human activities. So in this case, it is important for us to identify water concerns and how to address them based on the quality of the water. So this is important. So knowing the water quality will help us identify the water concerns and how to address them. It is a very critical part of managing our water catchments and management of our water, because basically the kind of water quality will affect the end use of water, how the water will be used ultimately, and it also influences the health of our hydrological system. So when we know water quality, we'll be able to know exactly what treatment processes we are going to do with them. For example, in a water treatment plant or in a wastewater treatment plant or even in desalination. So we'll discuss this more in the next few slides. So the quality of water will vary from place to place, or from source to source, or from season to season. So for example, the quality of seawater is different from the quality of groundwater. So the quality of surface water will also differ from the quality of groundwater or from wastewater even. So these things, it will really depends on where you are getting the water from, and also when are you getting the water from. So for example, the temperature during that time will also affect the water quality, because temperature is an important characteristic of water as well. So in overall, we can define, or we can present water in water quality in three different properties based on physical, chemical characteristics, and biological characteristics as well. So basically, physical is based on what we can see or from our senses, for example. So this is from what we can see, what we can smell, and this is more related to the public perception, because this is what the community or the people will actually be able to feel and taste, for example. So some of the physical characteristics are color. Of course, when you say color, the person would have that psychological thing about color as well. A clear water ultimately would mean for them as something that is safe to drink. You don't want to drink something that is like this, right? So having to see a color like this would eventually have that assumption from people that this is not safe to drink, which is in most cases is true. So this is a clear water in terms of color would signify a safe water or a potable water. Odor is another thing. So odor is something that you can smell. So I have an experience with this odor before when I went to the USA about a hotel which has some sort of a different odor when I entered the room. So the odor for them, I thought it was an old room, but then again I realized when I took shower, the odor was coming from the water. So the odor, because of an odor coming from the water, I assumed that was already not a good water, not safe water. But of course, it was only for shower. But I was assured that the odor was safe at least for external uses, not for drinking. And they have a separate process for drinking purposes. The other one, a bad odor will definitely signify a different case. So if you are smelling something like a rotten egg, then you would probably really think that something is wrong with the water. All right. So that rotten egg has to do with the H2S, hydrogen sulfide. So we're going to talk about that later on as well. And solids also, this will refer to the turbidity or the cloudiness of the water. So it's pretty much related to the color as well. So the turbidity like this is very turbid. The cloudiness and turbidity is different from this one. So the more solids like total suspended solids you have in the water, maybe it's suspended and including the dissolved solids as well, will determine the turbidity, especially the suspended solids, will determine the turbidity, and it is measured in terms of NTU or nephelometric unit. All right, so the higher the turbidity, the cloudier is the water. And temperature, of course, is something that would signify if water is okay to drink or not. Sometimes people, if we are getting a water source from, for example, our natural source, and the water is very, very hot, so we will think something about the temperature of the water as well, if it's safe to drink or not. So these are some of the physical properties or characteristics of water as part of the water quality. So it is related to public perception or aesthetic perception. So it's basically more as considered as aesthetic contaminants. So because they are referred to how it looks like or how it feels or how it tastes. So this is where most of our public are deciding if they are accepting the water as good or not. The other property or characteristics is based on chemicals. So what chemicals are inside the water? So chemical basically are is referred to the is related to the toxicity of the water. How dangerous or how safe is the water totally overall. So it's based on chemicals. So let's pesticides there, if coming from, for example, water coming from the irrigation, for example, there should be a lot of fertilizers and pesticides, some alcohols, for example, some heavy metals if it's coming from a mining industry. So we're expecting a lot of metals there, heavy metals, some phosphorus and nitrogen, which is related to fertilizers as well, and H2S, hydrogen sulfide, and methane. And so all of these will determine the toxicity of your water. And it can be determined mainly by a number of testing methods. And we call chemical testing for this one. And it's involved in most environmental engineers will be able to do the testing for this. And the last characteristics is based on biological characteristics or properties. And this is the characteristic that is related to the illness, the disease that could possibly be coming from the water, because these are more on the existence of biological matters like the decayed animals and plants, bacteria, and some viruses, for example. So the more content of these biological things here, the more dangerous the water is for consumption, because it will lead to you to some really serious diseases or illnesses. So we can define or we can differentiate two types of water. One is potable, and which is the A grade water, and one is palatable. So in these two differences, potable is basically something that is safe to drink, regardless if it's not so clear. Sometimes there are some water that is not too clear but is still safe to drink. Not is necessarily aesthetically pleasing. Sometimes you can still smell something, but it doesn't mean that it's not safe to drink. And potability is affected by these various characteristics like microbes or biological characteristics, some organic chemicals inside and inorganic chemicals inside as well. So depending on their level of their concentration in the water, as long as they meet this some standards, so it means that they are safe to drink and they are potable water. The other side is palatable water. So palatable is basically more on how it looks like and how it feels and how it tastes. So aesthetically pleasing. So it has to be clear, it doesn't smell at all, and also there's the temperature is just the right temperature. It's not too hot, it's not too cold. And even though there are chemicals there, it doesn't really pose a threat to human health. So it is at the level of a safe level, more or less. It could contain some of these constituents here, like chloride. It has some color, a little bit of color, some taste and odor. But basically, overall, it will look better. It will look in a good and pleasing way, and it is acceptable for the people. So these some of the pathogens and viruses that could be possibly be found in water. So if you look at the different types of microorganisms, for example, you have bacteria here with the different sizes. All right, so this is a bigger size from point 0.1 from 1 to 10 micron, for example, is the size of the bacteria. E. coli is around 2 micron in diameter and around 8 micron in size, in length. Some viruses are smaller in sizes. Some protozoa is bigger as well. Some tapeworms is much bigger, which could be possible be inside the water. All right, and depending on what sort of microorganisms and viruses you have in the water, it also depends on what kind of processes, treatment processes or treatment trains you will design for them, right? Okay, so some of the example diseases that were found in water and wastewater before were typhoid, cholera, and polio. Even hepatitis are there, and you have the diarrhea as well if you are drinking some polluted water. And some of the other most common bacteria that you can see, Escherichia coli or E. coli, and it will attack your intestines or your tummy. You have tummy ache here. Salmonella is typhoid fever, and Giardia lamblia is also something that was used to have an outbreak in Australia as well. So these are some of the common pathogens that will cause diseases if they are at a level that is not allowable in water. So we have to remove them, especially if coming from wastewater. So these are some of the potential sources of contaminants impacting water quality. So as I mentioned before, we have point source and we have non-point sources, and these one are basically more of a point source, more point source of pollution from different industries, from industrial wastewater. So we have petroleum-based industry, some refineries there. So mainly their water will include a lot of hydrocarbons. From metal-based industry, for example, mining, of course, if you are mining some metals, some materials, mineral sands, you will have a lot of heavy metals and a lot of sediments, all right? And then sewage treatment systems, a lot of nutrients and some suspended solids, and a lot of bacteria and pathogens there coming from wastewater, all right? So, and then you have some acid-based industry as well. So a lot of metals as well, some acidic solutions, which all in all will impact the receiving water. So if it is being disposed or discharged to the river, and so the river system will have a lot of danger there. For example, in this case, it could be dead fishes, for example. Even it's very harmful for the people if they're consuming it. Some of these, for example, most are on the degradation of habitat. So fish will also die. Excess nutrients from this side, if you have a lot of nutrients, then you will have eutrophication. It means the algal blooming, which is quite dangerous as it reduces the dissolved oxygen that you have in your water system. And so these are just some of the possible effects on receiving water. And there are some measurements that will be possible to see what sort of water quality you have. So we can do different water measurement in these systems as well. Water. And this is another example for domestic uses and urban land uses. So they have also different types of sources and different types of contaminants, like nutrients also for wastewater, hydrocarbons, and the same way. The loss or the potential effect on the receiving water would be quite bad. Not only for river, for example, if they are discharged to the ocean will also impact even desalination plant. If you have desalination plant in your urban setting, if you discharge your brine directly to the ocean, it will change the water quality of that specific place where you are discharging the brine, because brine is a concentrated, there's a very high concentration of salts, and if you discharge it into a specific area of your ocean, the salt concentration of that area will increase so much. And with the increase of salt concentration will affect the pH and the temperature balance. And changing the pH and temperature of a system will also affect the living organisms beneath that water surface, like the fish and some other organisms. So it will also impact the all of the life under the water. So we have to be careful about the impact of these discharges to the water quality. So in relation to the water and wastewater treatment, which is very important, that is why we are also trying to understand the importance of water quality. In a water or wastewater treatment process, we are doing these processes in order to make water acceptable for end use. So it depends on our end use. If it is drinking process, so we need to have more stringent treatment train. If it's for industrial or for irrigation, maybe lesser processes, not much stringent processes, because it's a different water quality. And basically, another reason for this water and wastewater treatment is to remove the contaminants, basically, that are not good for human health, like pathogens, as I mentioned, inorganic materials like arsenic, nitrates, some disinfection products which are harmful for human consumption, and to remove other contaminants in terms of for physical, aesthetic contaminants. So this is to improve the taste, or to improve the smell, to improve the color, the appearance of the whole. So this is basically why we are doing the water and wastewater treatment processes, and they are very much related to our water quality characteristics, right? So that's why we need to understand what are these water quality characteristics in order for us to decide what form or what processes are we going to design for each water quality and for each expected end use. For example, if it's using raw water, for example, which has a different water quality, which is a cleaner water quality compared to a wastewater, then we can decide a shorter train, like just the conventional water treatment train, from rapid mixing to coagulation to sedimentation, filtration, and then disinfection, and then distribution, because our source water has a better quality already compared to a wastewater. So in comparison to a wastewater, then we need further or more stringent processes, because they contain a lot of biological things and the BOD is quite high. So we will go towards a primary treatment, and then we go for a biological oxidation, which is needed because of the content of BODs is high compared to this kind of water. So the water quality is different. So So now we are doing this biological treatment because of the existence of biological BODs, all right, some biological things there. And then we go for disinfection as well, and then before some, it depends on what kind of use will follow. If there's for drinking purposes, for example, probably there will be further like reverse osmosis at the end in order to make the water quality acceptable for end use. All right, so for any water and wastewater treatment process, we need to identify the end use of water. We need to know the source and the source of the quality of the source, the water quality of the source, and of course we have to consider the overall economics. So when you say overall economics, we need to design a system that has the most economically feasible system with the best result to meet the acceptable water quality. So we don't need to put a lot of different systems in between anymore because that will add the cost if the water quality at the source is good enough already. So we don't need to put a lot of barriers here. With this, compared to a lot of barriers, if this system works, then that should be enough because we are also considering the economics of the overall system. So now let's talk a bit of some of the, how to say, important parameters, water quality parameters. There are many water quality parameters that affect the overall water quality. Some of these are pH, the hardness of the water, salinity or the salt content, total dissolved solids, or those that are dissolved that we cannot see exactly. This is different from total suspended solids, the temperature of the water, the DO or dissolved oxygen, BOD or biological oxygen demand, and of course the nutrients and some other things that are included in the water quality. But we will only discuss some of these, and the other details you should be able to read in the reading material provided. So let's start off with pH, and this is one of the most important water quality parameter that one needs to know. So basically, as we all know, pH is a measure of the content, the hydrogen ion content concentration, which determines the acidic or the alkalinity or basic quality of water solution. So it could be acid or basic solution, right? So we know that in a pH scale, based on this formula, which is the negative log 10 of the hydrogen ion concentration, so you can use this formula to calculate the hydrogen ion concentration, or you can calculate the pH of the solution if hydrogen ion concentration is known. So pH scale is basically, we know that the neutral pH is 7. So it's neither acid or nor alkaline. But below 7, we call it acidic. And around this part is highly acidic. And alkaline is those that are beyond 7. So 8 until 14. So the highest one is 14. So basically, if you look at some of the natural water that we have, seawater is usually at a pH of around 8 to 8.5 because of the presence of a lot of minerals and salts there. Fresh water is around 6.5 to 9.0 as a pH. And we think we have to ask about why it's 6.5, why it's not 7, which is the neutral pH. So normally, if you look at the pH of water, the pH of the surface water is normally it's around below 7. The reason for that is because of the loss or gain of dissolved carbon dioxide. So if you have a surface water, for example, and you expose this one to the atmosphere contains a lot of CO2s. And then some of these CO2s will actually dissolve in water, depending on the temperature of water. But in any case, at natural ambient temperature, CO2 will dissolve in water, and this CO2 will react with H2O. Okay, so when it reacts with H2O, the reaction will form into H2CO3, which is the carbonic acid. Okay, the carbonic acid will dissociate into a hydrogen ion, and the H plus will now be the one that makes the water acidic. So that's why, because of the formation of H plus, the water in this system is at below 7. So normally it's around 6.5, and even 5.6 is the usual pH value for surface water that is exposed to the atmosphere. So some of the drinking water guidelines for drinking water, pH is around 5 to 9. Irrigation water is for 4.5 for 9 pH, pH 9 as well. So other than this range, some problem will occur for humans, for example, or for plants. All right. And the importance of pH is also, aside from this one, the formation or the pH of water will change. It is also important to know the pH because it affects the chemical forms and of the system inside the system, and environmental impact of many chemical substances in water. All right. For example, if you have a low pH, okay, if you have a low pH, like for example pH 4 or pH 3, the ammonia inside the water will be in a form of ammonium ion. It will be in an ionized form. So this one is NH4 plus, an ionized form. An ionized form of ammonia is less toxic, okay, less toxic to human beings. So if you want to decrease the ammonia level in your water, you need to at least make it low in terms of pH, okay? But at a higher pH, the ammonia is in the form of unionized ammonia, okay? This nitrate here becomes NH3, and this is more of unionized, not ionized, okay? And this ammonia form is more toxic, but yet this is more volatile. So it means it's easier to evaporate. So if you have a lot of ammonia in your system, in your water, for example, and you want to decrease your ammonia level in your system, what do? Okay, the nitrate level, for example, the nitrogen level. If you want to decrease this one, then you want to treat your system by making sure that your pH is high. So you increase the pH of your water so that the form will be more of an ionized ammonia form, NH3. And then you subject your water into a stripping tower. Okay, so you strip the ammonia by adding some air to strip out the ammonia from the system. So that's why we have a stripper in the water treatment system, so that volatile ammonia will go out of the system and you are decreasing your nitrogen content. Or air stripping, or based on or by aeration. So this is why pH is just an example showing that the pH of the system will affect the chemical forms in the system. And so these chemical forms will definitely let you know what exactly to do with them. And example of this I've given you is about ammonia. Another important parameter is the solids concentration, and this refers to two kinds. This is the total suspended solids and total dissolved solids. So what is the difference between the two? So let's start with TDS. TDS is total dissolved solids, is what we call as non-filterable solids. So once we have a solution like a water solution, then we subject that solution into a 0.45 micron filter, all right, or 450 nanometer filter. So that 0.45 micron filter size, if you filter your water, anything that passed through that filter is what we call as TDS, or total dissolved solids. Anything that it remains on top of that filter, or those that are filtered, are called as total suspended solids. So what are these two? So basically, the total dissolved solids is the concentration of the dissolved substances, and the major contributors for this are the carbonates, bicarbonates, and many salts. So if you have very, very high TDS, it could be an indicator of the presence of harmful contaminants, just such as iron or some sulfate or some arsenic. But it can also doesn't really say that it's automatically harmful. It could be an indicator. But in general, even at high TDS, it's not really too harmful for the body but it could affect the taste, or it could have a laxative effect. It means that you go to toilet many times. So in this case, more than 1,200 milligrams per liter, which is the unit of concentration for TDS, then this could happen to you. But within 1,000 or below 1,200 milligrams per liter, or ppm, parts per million, it is more of an acceptable taste, or even the odor as well. Many of these TDS, total dissolved solids, come from human pollution, like especially those coming from runoff of irrigation, or the runoff from roads, and even from wastewater discharges. That's why TDS from this water quality are quite high. And in terms of the drinking water standard, in most cases, below 500 milligrams per liter is the recommended TDS level for drinking water. So at a higher value, it will have some effect in terms of the bitterness of the taste. Probably sometimes if it's too high, the odor will become not so pleasant anymore. And so this is a table showing that the different levels of TDS count in the water. And around this area here, from 150 to 500 would be an excellent choice for your drinking water. A maximum of 1,000 would be a recommendation as well. So TDS is an important indicator as well, for just to be an indicator of the quality of the water. So there are many different sources of this TDS. The other one is total suspended solids, or TSS, which is very related to the turbidity of the solution. So the higher or the more suspended solids you have, you will have this cloudiness in your water, and it is basically checked by a turbidity meter, and the turbidity meter will give you a value based on with a unit of nephelometric turbidity unit, or NTU. And for drinking water, it is as around 0.1 to 10 NTU, and the lower it goes at around 0.1 to 1 is the usual NTU. It says that it means that it is a clear water. So in our Australian water, usually our turbidity is around 0.1 to 0.5. So it's a very, very clear water, and it also says that the water is a potable one. All right. So basically, the suspended solids are these things: silt, some clay, some bacteria that makes the water cloudy or not so clear. And we have to at least know this kind of quality in order for us to determine what sort of processes we are going to do in a water or wastewater treatment plant. So turbidity, we can do some coagulation, flocculation, for example. And for TDS as well, we possibly use some reverse osmosis at the end to reduce further the TDS. When assessing water quality, temperature is one of the most important factors to consider. In fact, this is the most common parameter that is being measured during water quality testing. This is because temperature affects all other parameters in the water, and it all affects all the water uses as well. If you look at this figure here, temperature affects mainly many other parameters like dissolved oxygen content, the salinity of the solution, conductivity, the CO2 content or carbon dioxide content, the pH even, and some metabolic rates, and even the photosynthesis. Like for example, if you increase the temperature of a system, the solubility of gases decreases. And so it means that at a higher temperature, the solubility of oxygen, dissolved oxygen, decreases. The solubility of carbon dioxide decreases. It means that the oxygen and carbon dioxide is released from the system, is from the water. So that's why in cases where for example, a discharge from a manufacturing industry, normally these discharges are quite warm. And so it goes towards a discharge in a river, for example. So once it goes towards a river, the warm water will warm up the receiving water in the river. So that's why it also changes the temperature of the river. So we could refer to this as thermal pollution. So this thermal pollution changes the temperature of the system of that receiving water, and it also changes the dissolved oxygen in that receiving water, thereby affecting the fish and other living organisms in that particular water. So that's why we have to be careful about maintaining some temperature in order for not much changes in terms of the way the living condition of many animals or fish in that particular receiving water. Another thing is with regards to organic material. So there will be an increase of biodegradation, and when you have an increase of temperature, it will result to an increase of dissolved oxygen demand. It means that bacteria will be more active now, and they need more oxygen to biodegrade, to degrade the organic materials. So in this case, more oxygen, dissolved oxygen will be needed, and the demand will be much higher because of such event. So that's why it will also change the way the system works. And some forms in terms of biological, this one is biological, and chemical forms are also changed with the change in the temperature. As I've mentioned previously, with the change of pH, for example, the ionized and unionized forms of many of the chemicals like ammonia, hydrogen cyanide, and even H2S, the hydrogen sulfide, also changes with the temperature of the system. So that's why temperature is important. It's a very important parameter because it's basically a universal thing affecting all other parameters in the water. So no big changes in temperature will ensure non-deleterious or non-damaging effect to the aquatic life. The water hardness as a parameter refers to as is a property of the cations concentration in the water. Mainly the cations are mainly as in the form of calcium and magnesium ions. So calcium 2 plus and magnesium 2 plus. And while alkalinity, on the other hand, which is related to hardness, is basically the property of anions, carbonates and bicarbonates. So this is different from hardness. So for hardness, it's the cations. The alkalinity is on anions. So hardness is also an important parameter because this will let you know if your system will have the tendency for scaling. So at a higher hardness water, for a hard water, for example, the presence of calcium in the water, and then the carbonate ions, which usually are inside the water. So there's usually a carbonate ions inside the water. It will react with calcium and form into calcium carbonate as shown here. So the presence of bicarbonates in the water and CO2 in the water and calcium in the water will react and form calcium carbonate. And calcium carbonate, or in the solid form, is a scaling or scale, is when you see this one in your bathtub. If you don't really clean your bathtub, you will see some white scales or some this stuff over here, bath rings. These are usually calcium carbonate scales. Or another example, if you boil your water and your water is hard water. So I'm not sure if you have tried that one, but if you boil water with a hard water, then when you look at your kettle or the water heater, then you will see some white scales on the surface, and those are calcium carbonate. The same way, because that happens because calcium carbonate, the CaCO3, is basically an inverse solubility salt. It means that at a higher temperature, if you heat up something, that calcium carbonate will precipitate out of the system. It means it will solidify. So that's why at a higher temperature, if you boil water, it will solidify and become scale. And this is a problem because especially if you are using water, a hot water or a hard water in a cooling system or in a heat exchanger. So if you have a heated system and the system heats up that hard water, it could potentially form into scale. And this is like a form of scale. So what happens now is usually water should have this whole volume, this whole area of flow. So the volumetric flow of water supposedly is this the whole area of this. But because of the presence of scale, so now the area becomes small, the cross-sectional area becomes small, so the volume of water flow is also small. So in this system now, because of the presence of scales, you need to compensate for the the lower area, right? So you have to pump more water in order to have the same flow rate in the original. So once you pump more water, what happens is that you're using more energy and you are adding more cost in the system. So this is more expensive now because of that more pumping power. And besides, at the long term, after some time, if you continue using your um, hard water, these scales will eventually close up. And what it closes is means it's already fully clogged and blocked. So this one will now be a big problem if continuously used. So that's why we need to at least know as well about the hardness of your water. So some of the conventions here, when you say soft water, is less than 75 a milligram calcium carbonate. Okay, so this is the unit. This is based on calcium carbonate for hard water hardness. And if you also calculate alkalinity, is also milligram calcium carbonate per liter as the unit. And the hard water is around more than 120 milligram per liter, and very hard is around 200. So you want to maintain your water as moderately as possible, but not too soft. Soft water will also be not good because it means that this is also low in alkalinity and maybe acidic in form. So once you have a very soft water, if quite acidic, and then that means that if you use it in a pipe, in a metallic pipe, so the pipe could have corrosion as well. So maintaining a good hardness of the water is important for water treatment processes. Another very important parameter is in water quality is dissolved oxygen or DO. So DO basically is very important to maintain high quality water because it oxidizes objectionable sources of taste and odor. So this DO mainly refers to those non-compound oxygen or the free oxygen, the O2. So this one have two pathways, mainly two pathways. One is through the diffusion from the atmosphere, and the other one is by photosynthesis. So basically the diffusion from the atmosphere, as I've mentioned before, is through, for example, a wind blowing over a surface water, and the oxygen in the wind or from the atmosphere will diffuse through the water and dissolve and become dissolved oxygen. The other one is photosynthesis, and basically there are plants below the water, like for example underwater algae. And these plants, when once there's sunlight which can penetrate through the water, the plants will go towards a process of photosynthesis. And photosynthesis needs CO2 to consume CO2, and the byproduct is actually oxygen. So the oxygen remains in the water as in the dissolved form. So that's why it also adds to the overall concentration of oxygen in the water. So why oxygen is important? Oxygen is important because it's basically this is something that is needed for the survival of the fish and underwater animals. So the more oxygen, the better for the survival of the animals underwater. And basically, you need to have at least 8 milligrams per liter of concentration for a good quality water, and also for survival of these fish and other animals. In terms of its effect with solubility of oxygen and temperature, as I've mentioned before, it is strongly temperature dependent. So at a higher temperature, the oxygen solubility decreases. At lower temperature, the oxygen solubility increases. So that's why if you have that at cooler temperature, there is more oxygen in the water in the form of dissolved oxygen. But it is negatively correlated or inversely proportional to the amount of dissolved solids. So if you have more salts in the system, like for example, if you compare seawater and fresh water, the amount of dissolved oxygen in fresh water is much higher is higher compared to the dissolved oxygen concentration with seawater. So if more salts are there, it could possibly go down more. We can also see from this graph about the effect of the temperature. As you can see from here, the higher the temperature, the oxygen content is actually decreasing, which is pretty much relates to this dependence of oxygen solubility to temperature. Another thing with regards to the use of or to the presence of dissolved oxygen in wastewater. Normally in wastewater treatment plants, they require some oxygen level to help in the degradation of organic matter, especially in the biological reactor. So that's why the oxygen level usually in wastewater are not so high. That's why aeration is usually done to give more oxygen during the biodegradation of organic matter. And then the oxygen level also in community water supply, the higher is better. But if it's too high, what happens is that it helps in the speeding up of corrosion in water pipes. So that's why industries usually try to control the amount of oxygen in their water supply so that they will not lead into corrosion problems. So overall, dissolved oxygen is one of the very important parameters to consider in water quality assessment. The biochemical or biological oxygen demand, or BOD, is a measurement of the amount of oxygen consumed during biodegradation or used by microorganisms. This is an important parameter, an indicator to assess the effect of discharged wastewater will have on the receiving environment. So this means that when you have a higher BOD value, it means that there is also the greater the amount of organic matter or food that is available for the oxygen consuming bacteria. So in this case, if you look at this figure here, if we have a lot of BOD present in the water, and this green, the big green here is the bacteria, so this BOD will be consumed by the bacteria, and the white ones are the oxygen, because during consumption they need oxygen. So that's why the higher the BOD in the system, there will also be more need of oxygen for consumption in bacteria. So once this happens, if the receiving water has, for example, if the rate of DO consumption by this bacteria in the receiving water exceeds the supply of the DO from, for example, from the plants or from the photosynthesis or the diffused DO from the environment, then the situation will become unfavorable for the aquatic animals because more consumption and less supply. So as you can see here, this is the chemical reaction, the reaction of the use of dissolved oxygen plus the organic matter that is used by the bacteria. It results to biological growth. The bacteria will grow, or the microorganisms will grow and releases carbon dioxide. So this is important parameter. So that's why wastewater discharges are always controlled not to exceed at a certain level. Usually a target of 30 milligrams per liter, or around 80 to 90% reduction from the original BOD concentration in the plant is the goal, is the objective of the wastewater treatment plant. And if you have a direct environmental discharge, usually you have to go as low as 10 milligrams per liter BOD to make sure that there is no detrimental effect on the receiving water. For domestic sewage, the usual amount of BOD is around 100 to 400 milligrams per liter, and the target is to make it below 30 milligrams per liter at the output. BOD is usually measured using BOD 5, which refers to experimental test, an empirical test. And this test involves around 5 days of sampling. So you put a bacteria together some with nutrients in a container, and then it is incubated for 5 days at a certain temperature at 20 degrees Celsius in the dark. And then you measure the decrease in oxygen content, the dissolved oxygen in that container after 5 days of incubation. So basically, the decrease in oxygen concentration, the amount of that will be your BOD measurement. So BOD is basically a good indicator of how polluted the water is. So the higher BOD, it means that there's more pollution in the water system. And of course, the nutrient content in water is also a very good indicator of the quality of the water. And mainly these nutrients are in the form of nitrogen and phosphorus. So these are quite essential in our lives. Nitrogen is in the form of ammonia or nitrite and nitrate. So the nitrogen is here in this compound, NH3, NO2 minus, and NO3. And both of these nitrite and nitrate are very important for plants, but they are also quite toxic and dangerous for fish and animals. In fact, we need to limit the level of this nitrate and nitrite in our drinking water to less than 10 milligrams per liter, because otherwise it will be quite dangerous for human consumption. And also the nitrification and the denitrification process also happens during the secondary treatment in a wastewater treatment plant via the conversion of this ammonia to nitrite and to nitrate, and these two can consume oxygen during the process as well because of the use of the microorganisms to go with the nitrification process. And another thing is phosphorus. So phosphorus is basically, we can see phosphorus in our own body, in DNA, RNA, even in the bones as well. There's a phosphates there. And if we have, we need to limit as well the nutrient phosphorus into the receiving water if we are discharging, because high amounts of phosphorus in receiving water will be very detrimental to that receiving water. And in the process is the algal blooming. Basically, because of the nutrients, plants will grow very, very quick, especially the algae. And this is the process of eutrophication. It covers the whole surface of the surface water with algae. So once surface water is covered with this plankton here, it means that there will be lesser chance for oxygen from atmosphere to dissolve. And once oxygen is not dissolving in the from the atmosphere anymore, it means that your DO concentration below the surface will be diminished, and that with that it will affect the aquatic life under the water as well. So there will be dead fish. Even this one is just maybe possibly it can be dead later on, but eventually this kind of situation should be avoided and should be controlled in terms of controlling both nitrogen and phosphorus in the discharges. So those are some of the water quality parameters that serves as some variables, controlling variables that strongly or that influences the behavior of many other constituents in the water. So these are indicators of water quality, and they can be used in especially if you are looking at water and wastewater treatment processes, or if you're looking at the end use of water and discharge limitations. We need to consider these parameters for these water quality assessments. The water quality is then affected by some issues, especially by some events, like for example, in this case, bushfire. So we have a recent experience in bushfire in Australia, and the bushfire together with the rain after that bushfire has resulted to a number of pollution problems in water. So during bushfire, there will be a loss of plants and vegetation. The soil structure will be changed because, as you know, it's a very high temperature fire. It's a very hot temperature. So the structure of the soil on top of this will be definitely exposed to this high temperature. So there will be a change of the surface of the structure, which will lead to the changes as well to how it holds vegetation, and also in terms of erosion, because once it changes, it cannot hold anymore the plants, the trees, and so water can run off together with the sediments. So this runoff brings sediments and pollutants together, especially after bushfire when rain comes, and so there will be runoff, a lot of runoff, and it will go towards a water body. And the fire can also trigger some of the chemical reactions that are released that can release nutrients and metals and toxins from this part of the vegetation and soil. So also, if the fire is located in where water infrastructure are, for example, if it's near dam and the pipings are from the dams towards the supply pump pipes, so it means that the water could possibly destroy these infrastructures as well. So when the water infrastructure is destroyed, there will be leakage, there will be the infiltration of different pollutants and contaminants. So the water quality supply will also be affected. And of course, as I mentioned to you, the temperature of water is very, very important. And so if it's exposed to high temperature, it will also increase the water temperature, which will affect a lot of different variables or parameters in the water, as I mentioned earlier. So this will also be detrimental to the overall receiving body, for example, receiving water body. So normally after bushfire, there should be a number of water quality monitoring program because this will lead to a lot of pollution. Most especially what we have experienced recently, the rain, there's a lot of rain after the bushfire. And so that was also making matters worse because now the rain is bringing off the runoff with all these burned things and pollutants and other things going to our reservoirs. And then that will exert stress to our treatment processes, to our treatment technologies. And so that will be another problem. So there should be a water quality monitoring program to be done, especially after these events, to make sure that the infrastructure are made fixed again, the lines, the access tracks, and also to control the sediment and erosion during these bushfire events. So all of these will happen. For example, bushfire here, and if you have a water body, then all of this pollution will come into your water body and will affect not only the aquatic animals, but of course our treatment system may have a lot of stress and may not be able to completely and safely treat our water. So of course it has to be monitored well. Another event that could be affecting the water quality is black water event. So black water usually happens when flooding rain comes after a long drought. So for example, if we have a long-term drought, which means that it is a very dry land, there's a lot of decomposed organic materials. So the leaves are decomposing, the animals that died are also decomposing. So it means that the BOD, the organic matter, is increasing. So when rains come, just similar with bushfire, when rain comes, then they bring this organic matter and leaves together. And then if these are brought to a certain receiving water, and as I mentioned before, the higher BOD, and this is our organic matter, so this BOD will actually consume more or require more oxygen or demands more oxygen. So what happens? So if it goes to the receiving water, there will be quite a lot of loss of oxygen in that receiving water. And also added to that is the release of tannins in the water that makes the water this is from the organic materials, it will make the water turn black. It's like a dead water because of the depletion also of oxygen. So there is a lot of dead fish, and aquatic animals will be very, very much affected. So these are two of the issues that could affect water quality. There are other issues that you could identify, possibly the sulfate content or sulfate soils and other things that would possibly affect the water quality. And to give an example of some of the key water quality parameters based on Australian drinking water guidelines, we have different categories on physical, chemical, and microbiological or biological characteristics here. And we can see the different values required for the suppliers to follow in terms of the water quality. So like for example, turbidity should be less than 5 NTU. And as I mentioned before, the turbidity of our water here is around 0.1 to 0.5 or less than 1. up to 1. So this very clear water in Sydney. The color should be less than 15 HU. The content of iron should be like this as well, and some other metals here and minerals. And of course, the content of microorganisms should be as low as possible, or 1 CFU per 100 ml sample. And so this is expected in order for a safe drinking water. This guideline has to be met by most of the suppliers. So those are the things that we need to cover about water quality. Next video, we will be discussing about the various sources of water and how their quality are different from each other. For example, if we talk about groundwater versus surface water, what are the key differences in terms of their water quality? So these things we'll be covering in the next video.